Hey there, curious minds. Welcome back to the Deep Dive, your shortcut to being genuinely well-informed. Today, we're plunging into a topic that's really fundamental to almost every AI interaction you have. How do machines actually understand human language? We're talking about something called embeddings.
It's a fascinating area, yeah.
Hmm.
Because it's not just about computers recognizing words like keywords. It's more about them grasping the nuances,
Hmm.
the relationships, the context of what we say and write.
Exactly. I mean, think about it. Our devices can translate languages. They can answer really complex questions. Some even write poetry now. But how do they get from just a jumble of letters to actually understanding meaning? So, our mission today is to unpack that journey. We're drawing insights from a big survey on sentence representations and other cutting edge research, too. You'll discover how we teach machines to sort of think about words, sentences, even whole documents, and why this seemingly abstract idea is so incredibly practical.
Okay, let's unpack this then. Computers don't get words like apple or freedom, not directly. They understand numbers. So how do we bridge that fundamental gap?
Right. Well, this is where word embeddings come in. It's essentially about transforming words into numerical vectors, basically a list of numbers, yeah, in a continuous low-dimensional space. And the really fascinating part is that words with similar meanings or contexts end up positioned closer to each other in this space.
So it's kind of like creating a semantic map, a coordinate system for words where related words are neighbors. Precisely.
Yeah.
That's a great way to think about it. And this allows for what we call vector arithmetic. It's pretty cool. For example, if you take the embedding vector for king and you subtract the vector for queen and then add the vector for woman, you get something very, very close to the vector for man.
Wow.
Yeah. It shows how these embeddings capture relationships like gender or even like verb tense. You can maybe take walked, subtract walking, add swimming, and you'd land somewhere near the vector for swam.
That's incredible. So, okay, how did we even start doing this? Before these clever embeddings, I remember hearing about something simpler, like one-hot encoding.
You're right, yeah. Before embeddings, we had simpler but very limited ways. One hot encoding was one. Imagine a massive spreadsheet, basically, where each word was just a unique number in a huge list. It knew a word existed, sure, but it couldn't tell you if cat and kitten were related at all. It was high-dimensional, really scarce, and just completely lacked any sense of semantic relationships.
Okay, so not very useful for understanding meaning. Then came the breakthroughs, like Word2Vec, right? From a Google team back in 2013. What really kicked things off there? How did that change the game?
Word2Vec, yeah. With its models like skipgram and CBOW, continuous bag of words, it learned word representations based on local context. It was clever, actually. It would predict surrounding words from a target word, or the other way around. It basically figured out that, coffee and cup often show up together and started building numerical representations from those kinds of relationships.
Ah, okay. So Word2Vec showed us the power of local context, what's immediately around a word. But what about the bigger picture, the whole tapestry of language? I think that's where GloVe came in, from Stanford in 2014, a different approach.
Exactly, yeah, GloVe or global vectors. It ingeniously combined that local context idea with global statistical information. Specifically, it looked at word co-occurrence probabilities across an entire document or corpus. So it learned from how often words appear together globally, not just, in their immediate neighborhood.
Interesting. So we have these different methods. How did they actually stack up against each other in like real-world tests? Did one clearly pull ahead?
Well, yeah, there were studies comparing them on tasks like news classification, for example. If you are classifying news into, say, 20 topics, fast text slightly outperformed GloVe and Word2Vec. The numbers were something like 97.2% accuracy for fast text, 95.8% for GloVe, and 92.5% for Word2Vec.
97.2%. That's quite a lead for fast text.
So was it the undisputed champion of that era, or is there a bit more to it?
Well, while fast text did perform best in that specific comparison, the researchers noted the difference wasn't like crucially significant. But what's really fascinating about fast text and a distinct advantage is how it understands words. It breaks them down into subword units, kind of like syllables. This means it can actually create representations for words it has never seen before during training.
Oh, wow.
Yeah, it solves the out-of-vocabulary problem. Word2Vec and GloVe really struggled if they saw a new word. Fast text could handle it. That out-of-vocabulary thing sounds incredibly useful in practice. No model sees every word. But even with these leaps, there was still a big piece missing, right? Like the word bank. How would these models know if you meant a river bank or a financial institution? They just have one vector for bank.
Exactly right. That was the big limitation. These early models assigned a single static vector to each word, regardless of its context. That's the polysemy problem, words having multiple meanings. Those models just couldn't distinguish them.
So, okay, a word's meaning shifts with context. That seems obvious to us, but a huge hurdle for machines back then. How did embeddings evolve to handle that? That must have been the next big puzzle.
Absolutely. That limitation really paved the way for contextualized embeddings. The idea is simple in concept, but really powerful in practice. The word bank should have a different numerical representation depending on whether it's near river or loan. This was a massive leap. AI could finally start grasping the shifting meaning of words based on their surroundings. True comprehension was getting closer.
Right. So what came next? Which models really pushed things forward here, allowing AI to get that context?
This is where models like Elmo and then, the really big names like BERT and GPT started to truly revolutionize natural language processing, NLP. Elmo, for instance, used something called bidirectional LSTMs, long short-term memory networks.
LSTMs, right. Better memory than older network types.
Exactly. Allowing it to generate dynamic embeddings that changed based on the surrounding text. Different layers even captured different things like syntax or semantics.
And then, of course, BERT, bidirectional encoder representations from transformers. That really burst onto the scene around 2019. It felt like everyone was talking about BERT. What made BERT such a game changer?
BERT's real genius was, well, twofold. Its transformer encoder architecture and its unique pre-training objectives. Instead of reading words sequentially, one by one, BERT used this transformer architecture to look at the entire sentence at once. It considers words to the left and to the right simultaneously when figuring out the meaning, the embedding, for a specific word.
Ah, so it gets the full context in one go. That sounds like a fundamentally different and much better way of understanding text compared to just looking one way.
It really is. And it was trained using two clever tasks. One was masked language modeling, or MLM. Basically, they'd hide some words in a sentence, and BERT had to predict the hidden words based on everything else, the context.
Like fill in the blanks, but much harder.
Kinda, yeah. And the other was next sentence prediction, NSP. It learned to predict if two sentences logically followed each other. These training tasks forced it to develop a much deeper understanding of sentence structure, relationships, and meaning.
And the transformer part, that architecture, wasn't just about understanding better. It was key for speed, too, wasn't it? Especially with huge data sets.
Absolutely. Transformers can process entire sequences in parallel. Unlike older models like LSTMs that had to go step by step, that parallelism makes them significantly more efficient for the massive data sets and enormous models we use today. But what's fascinating here, host speaker, is that while these revolutionary models like BERT get tons of attention, the research, particularly this survey we looked at, really emphasizes that the data is just as crucial as the model itself.
Oh, interesting.
Yeah, it says, quote, most of the innovations have been concentrated in obtaining the right data for training these sophisticated embeddings.
So it's not just about building a smarter mousetrap, as it were, but just as much about feeding it the right cheese, the right information.
Exactly. The quality and type of data are paramount. A common technique for training sentence representations, for instance, is contrastive learning. The model learns by essentially being shown examples. It's trained to pull semantically similar sentences closer together in that vector space while pushing dissimilar ones further apart.
Okay, contrastive learning. Pulling similar things together, pushing different things away. Makes sense. But how do they get all this right data? Especially for something like contrastive learning, you need good pairs. Do humans have to label everything? That sounds incredibly slow and expensive.
It is. That's a huge bottleneck.
Right.
So researchers are getting creative. They're now exploring using other large language models, pre-trained ones like T5 or GPT-2XL, to generate massive amounts of synthetic training data.
Using AI to train AI.
Sort of, yeah. For example, in approaches like DNO, they use models like GPT-2XL to create pairs of sentences that logically entail each other or maybe contradict each other. This kind of synthetic data is crucial for tasks like natural language inference, NLI. That's where the AI has to figure out the logical relationship between two sentences. Does one imply the other, contradict it, or is it neutral?
Okay, synthetic data generation. That's clever. We've talked a lot about words and touched on sentences, but often we need to understand bigger chunks, paragraphs, whole documents. How do embeddings scale up?
Good question. Initially, the simpler methods involved just averaging or pooling the word embeddings within the sentence or document. You just take all the word vectors and average them out. It's computationally cheap, fast.
But I imagine you lose a lot of information that way, like word order, sentence structure.
You absolutely do. It can be problematic for understanding complex ideas. It's like, as you said, having the ingredients but losing the recipe. So that's why more advanced techniques were developed, often using those recurrent neural networks, RNNs, like the LSTMs we mentioned earlier. They process words sequentially, building up a richer, more contextualized understanding of the entire sentence or document as they go along. They maintain that order information.
Right, so sequential processing for longer texts. Now, this
Yeah.
also brings up languages. If machines can understand English this well, what about other languages? Can they switch between them? Or understand relationships across languages?
Yes. This is where cross-lingual and multilingual embeddings come into play. It's a really exciting area. The goal here is to map words or sentences from different languages into a shared vector space, a single map for multiple languages. A really powerful example is a model called LAMC Language Agnostic BERT Sentence Embedding. It supports over 100 languages.
Whoa, over 100. So wait, does that mean a French sentence and an English sentence that mean the same thing would actually map to roughly the same point in the shared space?
That's exactly the idea,
Yeah.
which is incredible, right? It allows for amazing cross-lingual tasks like semantic similarity, finding similar documents even if they're different languages, or cross-lingual retrieval. And this is especially vital for what we call low-resource languages, ones that don't have massive amounts of training data available like English does.
Shared meaning space across languages. Okay, my mind is slightly blown. But let's push it further. This is where it gets really interesting for me. It's one thing for AI to understand text, right? Abstract symbols. But what about connecting language to the physical world, like seeing an image and understanding it, or even controlling a robot based on instructions? How do embeddings make that leap?
Right, that's the frontier of multimodal embeddings. Multimodal meaning multiple modes, text, vision, sound, physical interaction. It's all about grounding language understanding in these other modalities, connecting the abstract symbols to concrete perception and action.
Okay, how does that work visually? How can an AI really see what words mean in an image?
So, for visual grounding, these models create joint embedding spaces. Think of it like that shared language space, but now it includes representations of images too. Images and text descriptions are mapped into this shared space. This is what powers applications like image captioning. You feed it an image, it generates a text description.
Like generating a cat sitting on a mat.
Exactly.
Yeah.
Or visual question answering. You show it an image and ask, what color is the car? And it can answer based on the image. And even things like referring expression comprehension, telling the AI, click on the red button next to the green box, and it can identify that specific object in the image.
Okay, that's already impressive. But robots. That still sounds like science fiction. How do embeddings help a robot understand pick up the blue cup?
It's rapidly becoming reality. Robots operating in complex, real-world environments need to integrate a ton of different sensor data. Think about 3D point cloud information. It's like a detailed 3D map of its surroundings from depth sensors. They get millions of little data points. They need to combine that with natural language instructions like grasp the blue object and maybe even data from their own physical movements, their trajectories. Multimodal embeddings allow the robot to learn shared representations that connect all these things. The visual appearance of blue objects from the point cloud, the concept blue object from language, and the motor commands needed to grasp. This allows them to understand instructions and, crucially, generalize. They can understand grasp the blue object and apply it to a new blue object they haven't seen before, adapting without needing explicit reprogramming for every single scenario.
Generalizing to new objects based on language and sensors. Okay, that is amazing. Now, this next part really blew my mind when I was reading the research. Are these AI embeddings, are they actually similar to how our own brains process language? Is there some kind of weird convergence happening?
It's a truly profound area of research right now, and the findings are pretty startling. Studies are revealing what they call a striking geometric alignment. Essentially, the patterns of activation in human brain areas associated with language like Broca's area show a remarkable similarity in their structure, their geometry, to the structure of these contextual embeddings generated by deep language models like BERT or GPT.
Wait, so the way the AI organizes language, meaning in its vector space, mirrors how our brains organize it. There might be a shared underlying structure, a common blueprint.
Precisely. That's what the evidence suggests. It's mind-bending. It suggests that these artificial embeddings might actually offer a computational framework, a model, for understanding how the brain itself represents language. They're even finding they can use these AI embeddings to make zero-shot predictions of brain activity for new words the person hasn't seen while being scanned.
predicting brain activity from an AI model.
Yeah. The really tantalizing glimpse into potentially bridging the gap between artificial and biological language processing, understanding our own minds through the lens of AI.
Okay, wow. We've covered some incredible power and potential here, from basic meaning to context, languages, vision, robotics, even the brain. But let's get practical again. With great power comes, well, often great computational cost, right? These models are huge. What are the real-world hurdles they still face?
Definitely. Practical challenges are significant. One major one is simply compression. These large embedding matrices inside models like GPT take up a lot of memory and require serious computational power. So researchers work hard on techniques like weight tying, basically reusing parts of the model more efficiently to save space, and quantization, reducing the numerical precision, sort of like saving an image at a lower resolution to make the file smaller, and also pruning, literally identifying and removing the less important connections or parameters within the model. These are all crucial to shrink these giant models down so they can actually be deployed efficiently, maybe even run on your phone or respond in real time.
Right, making them smaller and faster. But what about understanding why a model makes a certain decision? We hear a lot about AI being a black box. Can we peek inside these complex embeddings?
That's the huge challenge of interpretability, and it's a real issue. The abstract nature of these numerical vectors, these embeddings, makes it really difficult to understand exactly what specific information they're encoding beyond just knowing similar things are close together. Understanding why is vital for building trust, for debugging when things go wrong. And worryingly, there are even things called embedding inversion attacks. Researchers have shown it's sometimes possible to actually reconstruct the original text data just from its embedding vector.
Whoa, seriously? So the embedding itself could leak private information?
Potentially, yes. It highlights privacy risks. So the very compression and abstraction that makes them powerful can also make them vulnerable or opaque. It's a difficult trade-off.
So what's being done about that? How can we make them less of a black box?
Well, one interesting avenue is exploring using LLMs themselves to help explain. Getting models to generate explanations and narratives for embedding vectors, trying to translate those abstract numbers back into human understandable language.
Using AI to explain AI seems to be a theme. Okay, one last crucial area, bias. Given these models learn from vast amounts of text data written by humans, what about the potential for them to pick up our own societal biases?
Yes, that's a critical ethical concern, and unfortunately, it's a real problem. Embeddings absolutely can, and often do, inherit societal biases present in their training data. If the data reflects historical biases or overrepresent certain viewpoints or demographics, the embeddings learn those associations. They can perpetuate stereotypes. This means biased embeddings can lead to unfair or discriminatory outcomes when used in downstream applications, like hiring tools or loan applications.
That's really serious. How do we even measure that kind of bias within these abstract numerical spaces? And what can be done to fix it?
There are methods to measure it, like the word embedding association test, or WEAT, which looks for problematic associations, similar to psychological tests, and other statistical analyses too. As for mitigation, it's complex. It involves things like data augmentation, carefully adding data to try and balance out skewed representations, and also developing debiasing techniques algorithms designed to try and neutralize those biased associations within the embedding space itself, mathematically adjusting the vectors. It's an ongoing, very active area of research.
Wow. Okay, so from translating words into these numerical coordinates, these vectors,
Right.
to understanding context, bridging languages, integrating with vision and robotics, even mirroring human brain activity. Embeddings are really the silent powerhouse behind so much of what makes modern AI possible, aren't they?
They absolutely are, and they're continually evolving, driving advancements in just about everything, improving chatbots, making search engines smarter, enabling entirely new fields like embodied AI where machines can properly interact with the physical world.
It really makes you think. As these models get increasingly sophisticated at capturing the nuances of our language and maybe even aligning with our own thought processes, what does that mean for us? How might our own ways of communicating or even thinking change as we interact more closely with machines that seem to understand us better and better? Will we start talking to the machines differently, or will they truly learn to understand us, warts and all? That's something to ponder.